Hi, we'll be starting a new chapter called Thermal Effect. In junior secondary, I'm sure you have learned how to use particle theory, or we call kinetic theory, to explain the state of matter, solid, liquid, and gas. And so here is a simulation for you to explore. I'll put the link in the description below. So go and check it out now. And so what you can do is to click the state for that tab, and then you can see that you can change for different kind of chemicals. So you can got neon, argon, oxygen, and water. I'll prefer the best if you can go for water because this is the one that you are familiar the most. And here you can see the scale is 146K. You can change it to degrees Celsius, and you can also guess. I'm sure some of you already know how to convert from Kelvin scale to degree Celsius scale. But anyway, let's go for degree Celsius scaled. So according to your common sense, you know that the water, more precisely H2O here, should be ice because now it's negative 127 degrees Celsius, and icing point or freezing point is 0 degrees Celsius. So here, this is how atomic view of the ice look like. And so what I want you to do and observe is, you can also do it with your own simulation, and that is to heat it up, and obviously you can see the temperature will increase, and try to observe what happened. So now it's -5. I can see it kind of collapse for some of them. If I continue to do so, let's say 13 degrees Celsius, you surely know that go beyond the freezing point. That means now is really the water that we call. And try to observe how it looks like. And you can see that the structure earlier was having a certain fixed structure, but now it kind of separated, right? You can go from one to another, and you can slide through to one to another. And you can also see one of these kind of come out, and these effects can be seen more often when you go to a higher temperature, let's say 70 something. So you can see that the vibration go more vigorously, and there's one or a few of the particles will somehow leave the main group of the molecules. So I would like to ask you and think about what it is. Alright, the answer for these mysterious flying molecules is actually water vapor, and this process is caused by evaporation. And let's not mix it up with boiling. I'm sure you know boiling, and that is something you will have to see, the bubbling and the water turning into steam. But that only happened when you hit when you reach the boiling point, which is 100 degrees Celsius. And now you can see we don't, right? And then some of them is still coming out. So this is called evaporation, and the details of this will mentioned more later on. If you keep heating it up more, now it is something we call boiling, and you can see again they move more vigorously. They vibrate more vigorously, and then more of these molecules will turn into free electron, which is not electron, free molecule that is moving around because they are now in a gas state. And you can try harder if you want to. You can try to heat up more. Okay, so you can see this is exactly having all of these boiled, become steam, and you may see that they kind of free, but then at the same time they also spread out in the container, because since all of them become gas, then think about the gas pressure. They will try to spread out as much as possible to make a so-called equilibrium throughout the whole can, and this is the behavior that you should observe. The other thing that I will also want you to observe is try to go back to solid. Okay, again, this is a certain structure. You can see this is 2D, although like it's 2D. You can still see there's a certain kind of structure like a hexagon or something. And if you are really interested, go and search out how it looks like in a more 3D view in terms of the ice crystal. But anyway, what I want you to do is if you try to cool it down, you can see the temperature go lower. I want to ask you one thing. If I keep cooling it down, what will happen to the vibration? And so you may say that, oh, the vibration will get less and less. So let's see. And by the way, you can see that the temperature go more slowly. It decreases more slowly. And that's because we are approaching something called absolute zero. And if you try to look at the temperature now is negative 272 degrees Celsius. For some of you, if you read a lot of scientific books, you know that absolute zero is negative 273 degrees Celsius. So we are kind of 1 degree Celsius off from it. I hope you can see that if you can try to like look closer, that some of these particles are still vibrating. That means it still has a non-zero, should I say, non-zero kinetic energy. Right? That means it's not yet absolute, not yet absolutely zero. So if you keep cooling it down, and by the way, this is not realistic because you cannot use ice to make these colder, because unless you can have something that is absolute zero to make these happen. But then in laboratory, no one actually have reached absolutely negative 273 degrees Celsius. We get close to like something like negative 272 point something degrees Celsius. All right, because it's not easy, especially when you get to the very end of it. Anyway, so now you can see that this is a simulation, by the way, negative 273 degrees Celsius, and if you try to check carefully, each molecule, they do not vibrate at all. So this is the actual absolute zero, how it should look like in the simulation, and also according to a theory as well. So back to our notes, I would like you to put down the name of the state into the blanks. It's very simple, so pause the video and try it yourself.
A few moments later.
Alright, so I'm sure that you know the answer. This is a solid. Solid will have very strong force of attraction between the particles, and that's why to keep them close together. And they will form a fixed pattern, and that's why if you put them in a container, it doesn't fill the container, obviously. I mean, think about just putting ice into a glass of a glass simply. And so that doesn't look like the same when you fill water into a cup of glass, and that fill up the shape, obviously. Scientifically, we call that pattern lattice, and yeah, it can't change its position. The next one is obviously liquid, and they will have weaker attractive force than solid, and they will fill the container. And lastly, we have gas, and they almost will have no intermolecular forces. That means they still have a very small forces. They are the furthest apart in these three states, and they can move quickly, they can fill up the container in all directions and exert the equal pressure. And they will also collide with each other and bounce in all directions. And that's something I hope you have observed. All of these you have observed from the simulation just now.